A linear probabilistic model is useful specifically when the value of y is generally a linear function of x, hence the name linear probabilistic modeling. It is described using the model equation here where y is the dependent variable, beta sub 0 is the y-intercept, beta sub 1 is the slope of the linear regression line, x is the independent variable, and epsilon is the random error associated with each data point which corresponds to the vertical distance above or below the regression line. If epsilon is less than 0, this means the data point falls below the true regression line, and if epsilon is greater than 0, this means the data point lies above the regression line. It is important to note that since the error is random, epsilon itself has a normal distribution with a mean of 0 and a variance of sigma squared. The larger the variance is, then the further away the data points are from the true regression line. Since the random error associated with each point follows a normal distribution, the magnitude of the error and the probability of this error occurring are inversely related. Without the epsilon term, the model equation is simply just the equation of the true regression line, which represents the line of mean values. Here is a plot of some random data that clearly follows a linear distribution. Now using Excel, we can produce a linear regression line to model the sample data points. Excel automatically gives us the values for beta sub 0, which is 12, and beta sub 1, which is 4.6182. As you can see, even though all the points are generally close to the linear regression line, none of the points directly fall on the line. Because of this, they will all have a value for epsilon. For example, the first data point falls below the regression line, therefore its epsilon value denoted epsilon sub 1 will be negative. And for the fifth data point, its epsilon value will be positive because it lies above the regression line. In one of my previous classes here at UCF, an experiment was done that involved finding the Young's modulus for a beam and then determining the type of metal the beam is made of based on this value. First, strain gauges were placed on the beam to measure the strain. Then, using equation 1, we can determine the Young's modulus, and with this value, the stress acting on the beam can be found using equation 2. It is also important to notice, just by looking at equation 2, we can tell that the stress and strain form a linear relationship with one another, therefore making a linear regression line a good candidate for modeling this data. When we plot the data, the slope of the regression line is equal to the average Young's modulus, which is 6.47 times 10 to the 10th. By comparing this value with the known Young modulus for different types of metals, it was determined that the test beam was made from aluminum.